Alright, hello everybody, and this will be a bit of a shorter video. Today we're going to be going over how to represent a derivative mathematically. So in previous videos, we looked at this thing right here. This is just first principles. And specifically, we use this thing right here, first principles, to find the derivative of x squared. So we use first principles to find the derivative of a function, also known as the gradient function, because it in itself is also another function that tells us the gradient depending on what input we choose. So we have this idea of first principles here, where we're pretty much taking some kind of rise and dividing it by some kind of run to give us a gradient, and we're taking the limit as h approaches 0. So the limit as the distance between the 2 points we're comparing gets smaller and smaller and smaller to give us a more accurate result for our gradient pretty much. So really we're taking the idea of rise over run. And we're seeing what happens to this ratio here, this rise over run, as our h gets smaller and smaller and smaller. So if you do physics or chemistry, if you want to denote some kind of change in something, you would use the delta notation. So in this case, for our rise, we have some kind of change in the y values. So our rise is pretty much some change in the y values divided by some change in the x values, and this ratio here gives us the gradient. But notice one crucial thing here. We're assuming that these changes here are some kind of finite value, but the problem is if we use a finite value, then we're only going to get an approximation for our gradient. So that's exactly why we have this limit here. So if we're applying a limit to some small changes, then that means the distance between our 2 points we're comparing gets smaller and smaller. That also means that these small changes here get very, very, very small, infinitesimally small. So in calculus, we represent something getting really, really, really incredibly small by using the d notation. So instead of having a delta, now we have a dy over dx. Well, what does this mean right here? Well, you can think about this as being some really, really tiny small change in y divided by some really, really small change in x. And the ratio, rise over run, you can think about it that way, gives us the gradient, specifically the gradient of a tangent line to a curve. So this, in fact, here is what we refer to as the derivative of a function. So if we define, for let's say example, y is equal to x squared, then dy on dx, which basically says the derivative of y. So this is a y here, that's kind of like the function. So the derivative of y with respect to x. And why is this with respect to x? Well, it makes sense because x is the variable that we're dealing with here. So we're taking the derivative of y with respect to x, which is precisely the derivative of x squared. And in the previous video, we used first principles to find that the derivative of x squared was 2x. Another way you might see this derivative notation used is by having d on dx of y. And what does this mean? Well, here we're treating this d on dx here kind of like an operator. So if you have a d on dx, all it's saying is, well, find the derivative with respect to x of whatever is in front here. And observe one crucial thing here. This dy on dx can stand alone on its own because it's kind of operating on some kind of function already, namely y. But this d on dx here can't really stand on its own because it has to operate on something. It has to do something to something. A good example is like just saying sine. Well, what does that mean? Our sine here has to do something to something else, namely an angle or something. And that gives us some kinds of other result. Same thing's happening with our derivative here. So whenever you have a d on dx of something else, this is just saying take the derivative of whatever's in front here, and our function in this case is just y, so we're taking the derivative of y, which is 2x. Alternatively, you can see this notation used directly on the function itself. So if we want to find the derivative of x squared, we can just write it like this. So we're comparing a small change to the output of our function, which is kind of like rise to a small change in the input. So the derivative of x squared in this case is 2x. So all of this notation here is only when we're using y, if we're defining some kinds of y as, say, x squared. But another way you might see it written, especially if you define a function this time, so f of x, as being x squared or any function that we'll learn to take the derivative of, if we have f of x right here? Well, to find the derivative of f of x, we can just slap this derivative operator right in front, which says take the derivative with respect to x. So this variable down here is what we're taking the derivative with respect to. So derivative of f of x is exactly the derivative of x squared, which is 2x. So this is another way you might see it written in terms of a function. And one more little thing here, sometimes you might also see this written as f prime of x. And whenever you see this prime notation, all that means is, well, take the derivative of our original function. Well, our original function is x squared, so f prime, which is the derivative, is 2x. And this notation here is specifically powerful because this thing here is still in fact a function. So if we have f of x being equal to x squared, and we want to find the gradient at x equals to, say, -3, then we can just clearly express this as f prime of x, so the derivative evaluated at -3. And f prime of x is exactly 2x, so we have 2 times -3, which is equal to -6. So the gradient of our graph x squared at the point x equals to -3 is exactly -6, and this is why this f prime notation here is specifically quite useful, because you can just treat it like a normal function, just like with our f of x right here, where our f of x, we're inputting numbers into this function and we're getting kind of like the vertical values, the y values out of it. So whatever input we put into our function, well, we're just going to get the corresponding y value out the end. But however, if you use the function f prime of x, then instead of getting the y value out of the function, we're getting the gradient at that specific point out of the function. So that's pretty cool. So all of this notation here you'll see throughout calculus. There's so many different types of notations out there as well. These are just kind of like the basics. There's a lot of other crazy stuff like y dot, dxy, yx, and the list continues. But don't worry about this stuff right here. These derivatives are more so for other applications, but these are just kind of like the general forms of the derivative that you will come across, and which I'll be using in my future videos as well. So that's pretty much it for this one. I'll see everyone next time.